A very good morning to all. I am Mr. S.S. Sazni from Department of Mechanical Engineering, and I am teaching the subject Thermal Engineering. And today we are going to continue with our fourth lecture on the second topic from Thermal Engineering, which is ideal gases and ideal gas process. Now let's take a quick review of our third lecture, and then we will continue with the further points from this chapter. In our previous lectures, we have seen the important part from this chapter. So we have studied the gas laws, in which first we have started with Boyle's law. So we will just go through the statements of all these gas laws. So first we have started with the Boyle's law, which stated that the absolute pressure exerted by a given mass of gas is inversely proportional to the volume when the temperature is constant. So in short, we are remembering this as the product of pressure and volume is constant at constant temperature. Then again, the second law we have seen regarding Charles' law, and it states that the volume of a given mass of perfect gas, it will vary directly as the absolute temperature when pressure is constant. So again, we can mathematically remember Charles' law as follows, that is V is directly proportional to T, or we can also remember it as the ratio of volume to temperature will be constant if pressure is constant. Then we have seen the third law, that is Gay-Lussac's law. The statement for this law was as follows: the pressure of a given mass of gas varies directly with the absolute temperature of the gas when volume is constant. So for mathematically, this law can be represented as P is directly proportional to T, or in terms of pressure, we can also remember it as the ratio of pressure to temperature will be constant when volume is kept constant. So this was regarding Gay-Lussac's law. Then again, we have seen regarding Avogadros law. So the statement for this law was as follows: according to Avogadros law, equal volume of gases at same temperature and pressure will contain equal number of molecules. So for this also we have considered one example related the balloon, where we have seen that if equal volumes of different gases we have taken, then the amount of molecules that will be present will be same for each gas. So for the main condition that are required is nothing but same temperature, same pressure, and same volume. So if all these three conditions are satisfied, then whatever gases we are considering, those all will be having same number of molecules. So this was Avogadros law. Again, mathematically we also seen that the Avogadros law can be written as V is directly proportional to N, where V is nothing but the volume of gas, and N is the amount of substance of the gas. So these were the four gas laws which are very important from exam point of view, because I think that out of all these four gas laws, there will be definitely any one law will be asked in the MSBT paper. So since this part was very easy, so you might not be having any problem while studying these gas laws. Just the important thing is that you should remember the statement, and for remembering the statement you can take help of the mathematical formulas, as we have seen the mathematical formulas for each and every law. So after the completion of these laws, we have also studied one derivation which was called as equation of state. So this is also the question which is asked many times in the paper, and in this equation we have studied the relationship between variable parameters such as pressure, volume, and temperature. So in case of gas laws, we were just studying two variable parameters, and the third parameter was kept constant. But in this case, that is while deriving the equation of state, we have considered that the system will be changing from its initial state with parameters p1, v1 and t1. This will be changing to the final state where again the state will be having parameters as p2, v2 and t2. That means that we are going to change the conditions of pressure, volume and temperature, and then we are going to derive the relation between all these three parameters. So in this derivation we have considered two processes. One was a constant pressure process and the other one was constant temperature process. So for the first process we have applied Charles' law, and we know that in case of Charles' law the ratio of volume by temperature is kept constant. So for the first process we derived the equation in terms of volume, and then again in case of second process we have applied Boyle's law. Again we calculated the value of volume, that is VA, and after equating the right hand side of both these volumes we have finally calculated the relationship between pressure, volume and temperature. So this equation that we have obtained is very important from example point of view, because we will be going to use this formula while solving the numericals. So the equation that we have obtained was nothing but the product of pressure and volume, and the ratio of this product of pressure, volume to temperature, it will be constant. So you have to remember this formula, that is PV by T is equal to constant, and this equation is nothing but it is called as equation of state. Now we will start with the new point, and it is related with our previous lecture only, and that was the reason why I was repeating all these gas laws and the equation of state. So our new point is a characteristic gas equation. So again this equation is important for solving the numericals. Thus the characteristic gas equation for m kg mass is given as follows. So it is nothing but PV is equal to mRT. This equation is called as characteristic gas equation, and we have already derived this equation in the previous part, that is nothing but in equation of state. So there what we have derived, that the product of pressure and volume and its ratio with temperature is nothing but constant. So here we are in this characteristic gas equation, we are just representing the value of constant, and it is nothing but it is equal to capital R, where R is called as characteristic gas constant and its unit is joule per kg Kelvin. So for characteristic gas equation you just need to know the equation of derivation of state, and in place of constant we have to just replace that constant by the value of capital R. And again while deriving the equation of state we have considered that the mass of kg was 1 kg. So in case of characteristic gas equation we are not considering that the value of mass is 1. So if we are considering that say certain any amount of gas, and we are representing that any amount of gas nothing but equal to m. So you can see that in this equation we are having the same formula, that is PV is equal to mRT. So in case of equation of state, whatever the denominator was having, that is temperature, that is just taken to the right hand side, and in place of constant we have replaced that constant by R. And since instead of 1 kg we have considered certain amount of gas, that is m kg of mass, so we are also having this value, that is m, on right hand side. So we will see what are all these terms involved in this equation once again. So PV is equal to mRT is the characteristic gas equation, where P is nothing but pressure in Newton per meter square, V is volume in meter cube, M is mass of gas in kg, T is the temperature in Kelvin, and finally R, as earlier I told, it is nothing but characteristic gas constant in joule per kg Kelvin. So this was characteristic gas equation. Now we will study some more about the characteristic gas constant, that is capital R. So when we were deriving the relationship between pressure, volume and temperature, we have found that the ratio of pressure and volume to temperature is constant, and this constant is nothing but we call it as characteristic gas constant, represented by capital R. But it is important to note that if we are considering different gases, then the value of this constant is also changing. Like for air, we are having here two examples in this slide. So if we consider air, which is nothing but a mixture of different gases, then for air, the value for this characteristic gas constant is equal to 287 joule per kg Kelvin. However, if we consider pure oxygen, then in case of oxygen, the value of this characteristic gas constant, it is equal to 259.8 joule per kg Kelvin. So the value of R, it will vary depending on what gas we are going to consider, as well as what mass we are going to consider. And along with this, it will also depend on the parameters, that is pressure, volume and temperature. So we can just understand this with the help of the given formula, that is R is equal to PV divided by M into T. Again, for exams, they might ask you regarding what is the value of R for air, and also they might ask regarding the unit of the same. So you have to remember the unit of characteristic gas constant, and it is nothing but joule per kg Kelvin. So this is again an important question. In relation with characteristic gas constant, we are having one more concept which is called as the universal gas constant, or we also called it as molar constant. For this point, we have to study what is the definition of universal gas constant, what is its mathematical formula, what is its unit, and the value of universal gas constant. So these are the points which are asked in MSBT paper. So we will see this. As up till now, we have studied that the characteristic gas constant, which is nothing but capital R, it is always going to change with different gases. So the value of R is dependent on that particular gas, and for uniformity, we are going to replace this characteristic gas constant by universal gas constant. So we are representing the universal gas constant as R bar. So you should remember this difference between R and R bar. So if R bar is given, then it is nothing but universal gas constant, and if only R is given, then it is called as characteristic gas constant. Now if we see the definition of universal gas constant, then simply it is nothing but the product of molecular weight and characteristic gas constant. So we can see this definition in the given statement. The value of R is varies for each gas, and for uniformity, R is replaced by universal gas constant, which is the product of molecular weight and characteristic gas constant. So this is the definition of universal gas constant. We can mathematically represent this as follows, that is R bar is equal to R into M, where R is characteristic gas constant and M is the molecular weight of that gas in kg. Now again, the unit of universal gas constant, it is equal to joule per kg mole Kelvin, and the value of universal gas constant, it is equal to 8314.3 joule per kg mole Kelvin. So you should know all these points related with this concept. Now let's see one simple numerical based on all these concepts, that is characteristic gas constant and equation of state. So let's solve this question. So the question is as follows: a gas having 0.56 cubic meter volume at a pressure of 3.95 bar and temperature given is 30 degrees Celsius is compressed to 25.6 bar. The final temperature of gas is 370 degrees Celsius. Determine its final volume and also find mass of gas if gas is nitrogen with R is equal to 296.87 joule per kg Kelvin. So we have already now studied that R is nothing but characteristic gas constant, and they have given the particular value of R, which is 296.87 joule per kg Kelvin. So they have given nitrogen gas. So as we have studied that the R will be having different values if the gases are different. So there is no need to study this value of R for all the gases, but I would suggest you to at least remember the value of R for air, because this value of R can be asked in theoretical question. So for the rest of the gases, if we are considering the numericals, then while solving the numericals, they will be definitely giving this value of R for different gases. But at least for air, you should know that the value of R is nothing but 287 joule per kg Kelvin. So just remember this value of R for air, and for the rest of gases, they will be giving you. So let's note down what are the given parameters, and then we will solve this question. So they have given, if we read the first line of this given numerical, then there itself we are having about three values. So first they have given the initial volume, that is V1 equal to 0.56 meter cube. Then again they have given initial pressure, and that is equal to 3.95 bar. So we will be having this value as P1 is equal to 3.95 bar. Again we are having temperature also. So the initial temperature, that is equal to T1 is equal to 30 degrees Celsius. But while solving the numerical, we are going to convert this temperature from degrees Celsius to Kelvin. And for this conversion, we are just adding 273 to the given temperature in degrees Celsius. So the initial temperature, that is T1 is equal to 30 plus 273, that is equal to 303 Kelvin. So while solving the numerical, we will be just having or substituting this value of temperature, that is equal to 303 Kelvin. Now again the remaining parameters, then they have asked for final volume to calculate, and then again we are having final pressure, that is P2 is equal to 25.6 bar, and again final temperature also they have given, and that is 370 degrees Celsius. So again we are converting this degree Celsius to Kelvin, and so we will be getting the final temperature T2 equal to 643 Kelvin. Now if you have read the entire question carefully, then you might notice that in this entire question we are having all the values of pressure, volume and temperature for initial condition, and for final condition we are having the value of pressure and temperature, only the unknown parameter is volume. So from this you should understand that what formula we are going to use, since in the entire question they have not even used the word constant. So you should know that this question is not at all concerned with any of the gas laws. Then again you should also note that they have given different values of pressure, volume and temperature. So this means that all the three parameters are changing, and if all the three parameters are changing, then definitely this question might be related with the equation of state. So as per the equation of state, we are having formula P1 V1 divided by T1, and this will be equal to P2 V2 divided by T2. So whatever the values they have given, we will just substitute these values. So we will be having as 3.95 into 0.56 divided by 303, and this will be equal to the final condition of the gas, that is a pressure 25.6 into unknown volume. So we will be keeping as it is, and this will be divided by 643. So the value from this calculation, we will get the value of V2, and this value is nothing but it will be coming out as 0.1834 meter cube. So I would request you to solve this problem and just verify whether you are getting this value or not. After calculating the volume, again they have also asked to find the mass of gas. So for calculating the mass, we know that in case of equation of state, we have considered mass equal to 1 kg, but here we are supposed to find the value of mass of gas, and for this purpose we have to use the characteristic gas equation. So as we already have studied, this characteristic gas equation is given as PV is equal to MRT. So we will be putting or substituting these values in the equation PV is equal to MRT. Now while solving this, we can consider either the initial conditions of the gas, or even if we consider the final conditions, then also it is okay. So for now we are considering the initial conditions of pressure, volume and temperature. So we will be substituting the corresponding values. So we are having the equation here, P1 V1 is equal to MRT. So the value of P1 we are having as 3.95 bar. We are going to multiply this value of pressure by 10 raised to 5, so that we will be converting this pressure into SI unit, which is nothing but Newton per meter square. So again, this is important to note that while solving the problems, whatever the values are given in the question, we are supposed to convert that into the SI unit. So for initial parameter, that is while calculating the volume, we have not converted pressure into SI unit, and the main reason for this was since we were supposed to be taking the ratio of pressure for calculating the value of V2. If we convert that pressure into SI unit, that is we were supposed to multiply that value of pressure by 10 raised to 5. But if we multiply P1 by 10 raised to 5, then again if we multiply P2 by 10 raised to 5, then that was going to cancel each other. So whenever we are going to take the ratio, then in such particular cases there is no any such requirement that we were supposed to convert it this pressure into SI unit. But it is better that while solving the numericals, you are converting the entire parameters into their particular SI units. Like for example, in this question, they have given volume in SI unit, that is meter cube. However, the pressure is given in bar, so it is expected to convert this pressure into its SI unit, that is Newton per meter square. And again, temperature given was in degrees Celsius, so already we have converted that in SI unit, which is nothing but Kelvin. So just take note of this, that we should convert this pressure into its SI unit. So we have to just multiply the given pressure by 10 raised to 5. So now let's see how to calculate the mass of gas. So according to the characteristic gas equation, we will substitute all the values in this equation. So the pressure, so in this particular equation, you can see that we are having only one value of pressure. There is no any pressure value on the right hand side. So if we are just substituting the value in bar, then the entire equation will be not in SI unit. So we are supposed to convert this value of pressure into its SI unit, that is Newton per meter square. And thus we are multiplying the P1, that is 3.95 into 10 raised to 5. Then again this will be multiplied by V1, which is nothing but 0.56, and this will be equal to the unknown mass which we are going to calculate, multiplied by characteristic gas constant, which is given to 96.87, and multiplying again this by T1, which is 303. So by solving all these equation, we will be getting the value of m as 2.459 kg. So just as homework, you can also calculate the same mass just by substituting all the values of final conditions. So even if you substitute now all the values of final condition, that is P2, V2 and T2 in this characteristic gas equation, then also you are definitely going to get the same value of mass. So it's based on you. Either you are going with the initial conditions of pressure, volume and temperature, or you are going with the final conditions. But by both the methods, you will be getting the same value of m. So this was the numerical based on characteristic gas equation and equation of gas. So we will stop here now today. So just revise all the points whatever we have studied up till today, because all these points are necessary when you are going to study the further points from this chapter. So till then, thank you very much, and also stay home, stay safe.